Oh, see the cat? Okay, great. This is science progressing one funeral at a time. Okay, this is excellent. I had a great time. I don't know about you guys in general this week. Did you guys enjoy yourselves?
Yeah.
Woo! Woo! And I have to take a picture of all of you because then otherwise I now have to smile. See, it doesn't replicate. Woo! All right, excellent. Thank you.
We'll do also.
I feel like
somebody remind me because I'll forget. But we'll group photo as we go to lunch from there at some point.
This is great. What is going on here?
Your display is very upset.
My display is very upset. Okay. Is this better? No.
This could be the connector or something?
Okay, let me just do this. And this. I don't know what that is. Is it worse?
Now the text is wiggly too.
Yeah. You can take a new laptop and like launch the Docker on it.
I will. Yes. You are laughing, but I know people who wanted to do that. Okay. Anyway, we'll have to live with that. I guess. Okay. So before I begin, I want to tell you about one more initiative that we started to attempt to make replicating studies a bit more attractive to researchers. And this is the OHBM Replication Award, which was announced a few months ago and will be given out for the first time during the opening keynote at OHBM next year. And the idea is very simple. It's the best replication of the year, and the first time round this is going to happen. It's going to be the first replication of the past. So all of the previous papers count. And just to clarify, we're talking about attempted replications, not necessarily successful replications, and will be evaluated on various different dimensions, such as the quality of the research, as well as the impact of the question being evaluated. And another interesting detail that might help you decide to submit is that those do not have to be peer-reviewed papers, because we know how hard is it to publish attempted replication. So those could be just preprints on arXiv or bioRxiv. So it's an excellent way, especially for the first edition, because I don't expect that much competition, to dig up those replications from the drawer, write them up, put them on a preprint server, apply, and then bask in the glory. All right. So remember, OHBM Replication Award submissions will open very soon. All right. So now I'm gonna start this. Okay. Da-da-da. All right, great. It doesn't flicker. It's great. It's fantastic. So I'm going to talk a little bit about managing and organizing data now. But to do that, I would like to introduce you to Professor Smith. Professor Smith is up-and-coming, hotshot scientist, always at the lookout for new ideas and new projects that she can do with her excellent team. As you can see, she's very busy. And she recently...
I'm not actually a professor, by the
way. But everything else checks out, yeah? By the way, drop the paper there.
Yeah.
And the hypothetical as I said, always on the lookout for new ideas, new ways to move science forward. And she recently had this idea where she would use eye tracking as a proxy of attention, basically trying to figure out if people are dozing off or not during resting state scans. And for that, she realized she doesn't need to acquire new data. She can just reuse the data that one of her PhD students acquired a few years ago because she was doing some other study, and they just added eye tracking into that was never used. So what she needs to do is basically grab this data and put her new postdoc or a new PhD student on this project, and basically, yay, a new piece of science without the cost of acquiring new data. So let's meet the PhD student who acquired the data. This is Mike. So Mike graduated a couple years ago and then went to Silicon Valley and joined Uber and became a statistician, data scientist. So Mike is surfing in California right now, and he's unreachable. And Professor Smith, or Dr. Professor Smith, is trying to figure out where the data is, how the data is organized, and she comes up, finds this, external hard drive with maybe some DICOMs, maybe some nifty files, maybe a half-baked Excel spreadsheet, and she's basically lost in this disorganized heap of data. And anyone who was trying to look at someone else's data that was not intended for any type of sharing, whether it's within a group or with an outside group, can relate to this problem. And why is that? What problems does it cause? It's not only problems in sharing, and as I said, even within a single lab, every person will have different practices, but also it causes unnecessary manual metadata input. So when I try to run, for example, a pipeline on it, I have to dig up, what was the slice timing for this data set, or what was the flip angle for this thing, what was the phase encoding direction, and I have to find all this metadata, and now I'm trying to call up the MR physicist who was acquiring it back then because the protocols are not there, and I'm just lost. And it's also hard to validate those data sets. So basically, when you are running a group and someone leaves to California to start surfing and analyzing data, can you, in an easy way, figure out if the data set they're handing off is complete and consistent? That is hard without some kind of a standard. But there is some hope. MRIs has been used for many years in human brain imaging for over 20 years, especially when we talk about functional imaging. But even though there are so many similarities between experimental design and different data types that people acquire, there is little consistency in how we describe data sets. But those similarities in experimental designs and types of data come from the fact that we are using expensive machines that are produced only by a few companies in the world. And that's why it's easier to keep them consistent, and our workflow is very digital as well. So the data we acquire is already digitized in most cases, especially when we're talking about the brain. So it's not that we go in the field and we have this like grid and then we count number of ants on the ground, as in some fields you would have to do, and then we have to digitize the data. So we're in a very preferential situation where we can do some cool stuff. So we have kind of realized that and decided that it might be the time to bring people together and come up with a new way of organizing data, a new standard. And this standard before we began, we tried to figure out who's it for, and as I tried to explain, it's for the lab PIs, for people who are managing data acquisition, managing research, but also for workflow developers, because if you can assume that the input of your workflow/pipeline is organized in a specific way, it's much easier to figure out, where are the T1s, where are the DWIs, what's the field map for this scan, what's the slice timing for it, etc., etc. You don't have to ask these questions to the user and then face errors. It's also good for database curators, so if you decide of the off chance of ruining your career to publish your data to a repository such as OpenFMRI, please do. It's much easier to curate this data and merge it with the existing data sets. But it's also for you, because if you use this standard, there's a growing set of tools, and I'm going to talk about our latest effort called BIDS apps that accept BIDS compatible data sets and make data analysis much easier for those predefined canned pipelines and workflows. We had a few principles when coming up with this. Basically, we wanted this to be used by other human beings, so adoption was very important for us. We didn't want to reinvent the wheel, so we want to try to use common standards and file formats, things that people are used to, things that already are supported by different pieces of software. We also had this 80-20 rule, where we wanted to focus on the most common scenarios, most common designs. Those would account for 80% of different types of experiments out there, but leaving some flexibility for the 20% of those bit more edgy experiments and types of data to express themselves and eventually merge that into the standard. We also wanted to make it very community-driven, so we had a bunch of meetings. We presented first at Neuroinformatics Fora, and then at OHBM. We had release candidates and public call for comments. I've sent a lot of emails, and I also received a lot of emails. We've reached over 5,000 researchers. Some of them replied, and exchanged hundreds of emails, as I said, produced examples. That was also very important. So we took data sets and tried to see, okay, we converted, how does it look? Can we write pipelines to use it, etc., etc. And finally, we made it a bit more formal or official by writing and publishing a paper, and lots of people were involved, so the paper has lots of authors. So what is it? Basically, it's going from whatever your scanner outputs, and those could be DICOMs, but not all scanners output DICOMs. Those could be PAREC files, etc., etc., into a nice and neat structure of folders and files. And that structure is fairly formal, and you have a subdivision into participant folders, different modalities of scans, and additional metadata. So for tabular type of data, we use the good old tab separated value files. So it's very simple. It's nothing fancy. It's basically a text file with a header and values delimited by tabs. For binary imaging data, we've used Nifty, and that decision was highly discussed because Nifty has its limits, and there are other standards that do not have those limits, but have other limits. And the major factor in this decision was that 90% of the existing neuroimaging software can read Nifties, and we want to have a standard which would allow you to take this data and start working with it without having to do some conversions. That may be changed in some backward incompatible future release, but for now we're sticking with Nifty. But Nifty doesn't have all of the metadata we want, so that's why we are adding sidecar JSON files, and those are again very simple text file. JSON is a standard that is used heavily in computer science, so there are lots of tools for reading and writing and validating it, and we just use it for storing a key value store with metadata for the files. So this is basically it, and of course, there are many more details. There are many different modalities that you can describe using this, and each of them will have different specifics. I'm not going to go into that, but providing examples and a long, boring document wouldn't be quite useful because people don't read long, boring documents. So we also built a validator. So who was at the demo yesterday for the, I gave a demo, okay. So in that demo, I was uploading a data set to new version of OpenFMRI, and that data set, before it was transferred to the server, was validated. And this is exactly the same validator. And this validator checks whether your data set is bits compatible, whether it's consistent, and also does some simple quality checks. For example, checks whether all your subjects are acquired with the same scanning parameters, and gives you a warning if not. That's something that is surprisingly often overlooked when, you know, a technician pressed a different button and suddenly a resolution changes halfway through your study. The validator comes as a command line tool you can run on the server, as well as a web application. So you just go to a website, you don't have to install anything, you point to a folder and it validates it. So that allows you to implement this specification in your lab very quickly. You don't have to install any tools, you just look at a couple of examples and try to follow the scripts. There's a growing number of tools that are already supporting bits, and I'm going to talk a bit more about them in a second. And the advantage of having a tool that accepts bits is that using them is very simple, because you basically point to a bits folder and the application knows everything about data from it, because it knows where different data types are, it knows what different scanning parameters are, etc., etc. So, wrapping up a little bit, going back to Professor Dr. Honoris Causa Multiple Smith. In the future, learning from her mistakes on not imposing a certain format or structure on storing data in her lab, Professor Smith will be able to reuse data acquired in her lab much easier by conforming to a bit standard or something similar. So I'm going to go now and show you the validator maybe first. How are we doing with time? Professor Dr. Satra? All right, we're okay with time. Okay, so this is the bits validator. It's a whoa. It's an open source project, so you can say that you want a new feature, you can contribute new code, but we have developers working on it as well, so we can help you. You can install it as a command line tool, so I can go and do bits validator and say the yep. And I can validate the data set, and it'll tell me that this one is okay, but it has some warnings. For example, some scanning parameters differ. I can make it more verbose, and will tell me a bit more. For example, oh, this one has 34 voxels in the third dimension, but most of them has 33, and etc. But you know, this is command line. It's scary and it's off-putting and it gives me nightmares. But I can go to a website, and this is the bits validator on the web, and I can choose a folder and point to a data set. Sorry, just being a bit retarded. Point to data set, and it validates it, and you can see that there are some errors, and there are some warnings. And this happens instantaneously. This happens client-side. I'm not uploading any data. I'm not sharing any data. I could unplug a cable if it wasn't wireless. That would prove something, but it is wireless. So anyway, you don't have to worry that you're sharing any private information or data set that you're not willing to share. So this is a bits validator, and that's hopefully something that will help you adopt bits in your lab. So, and most recently, around a month and a half ago, we started something called Bits Apps. So it's a very simple idea where we take existing pipelines, and there have been quite a few excellent pipelines out there like CPAC, NIAC, HTTP pipelines, FreeSurfer, SPM, FSL, etc., etc. Lots of different methods out there to try out and use in your data. So we are taking them, putting them into containers, because all of them are usually hard to install and they have all these different weird dependencies, so it's sometimes a pain just to get them running. So we put all of their dependencies into containers. For those who went to a Docker tutorial, that might be a bit more easy. Basically, just put all of the binary dependencies in a way that creates a single package that you can download. So we put all of the dependencies in a container, and then we write either extend the pipelines to support bits, or write wrappers that take a bits data set and figure out, for example, for FreeSurfer, where are the T1s? Are there multiple sessions? Should they run a longitudinal pipeline, etc., etc.? And what you end up having is a single command line thing that takes a bits data set and then runs a given pipeline. So we are only just starting, but we have some tutorials on how to run them. So basically, if you're using Docker, you have to mount a couple of volumes, and then you specify what is your app, and then you point to a bits data set, you point to where your results should be. And then you can, if you want, you can specify, oh, I only want to run, first 10 subjects, or all of the subjects, or only one subject, etc., etc. And all of those bits apps are not only Docker compatible, but they also run on clusters. So we're using Singularity, and all of these apps are tested to go through this conversion, and you can convert them to Singularity and run them on your cluster, because many of them require lots of computational power. So running on your laptop is not very feasible. And we are we managed to get quite a few people to help us building those apps, and it's an ongoing process. So not all of them are passing the tests, etc., etc. But since it's only been a month and a half, I think it's a pretty good outcome. And if you're developing methods, this might be a very attractive way for you to distribute it to people. Because it's basically very, very easy. You just basically type, I can do Docker run let's example, oh sorry, demonitis, huh? Yep. Right, for interest of time, I'm not going to fix that, but basically just do Docker run, type to an app, and we automatically download it for you and kept there for reuse. All of them are strictly versioned, which is another very cool reproducibility feature. So when you, for example, running a longitudinal study, and you want to keep the same pipeline for example, a year and a half, you've got that reference, and you know that this whole package with all of its dependencies and all of the different pieces of software in it will not change. And you are in control of it. It's not up to administrators of the machine you're using to update those. And you can also go back to historical versions, and when you publish your paper, you can say, oh, I used FreeSurfer as a bits app, version this and that allows anyone to grab exactly the same copy of your environment and be able to reproduce your results. And to sum up, bits apps is a way of capitalizing on the fact that you already have your data in bits and running common workflows and pipelines. And we hope that will encourage even more people to use bits. And if you're a software developer, please get in touch and we'll get you going to create your own bits app. It's very simple. Those repositories, for example, this is the one I've been working this week on. are very simple. There's a short run script, and there's a Docker file, and that's kind of it. And in Docker file, you can do whatever you would usually do to set it up, to install software, and you decide which versions you install. You're basically king of your castle there. Okay, so let me go back to the slides. Woo. There are a few acknowledgements. I would like to thank my lab and my collaborators, Laura and John Arnold Foundation, who are paying for this, and Data Sharing Task Force for INCF. Lots of co-authors, as I said, and basically leave you with the website where you can find links to all of these initiatives. And just before I finish, let me just put that in the broader context. We hope that by setting better standards, even internally, it will make it easier for people to share stuff, not only within the lab, but across lab, with their collaborators, etc., etc. And that basically will make everything easier. And the platform we're building adds even more incentives to share, because we want to provide science as a service in exchange for making your data publicly available to everyone. So this is our big vision, and this is just part of it. So that's all from me about BIDS, and now Dr. Satra will show you how to use the HudiConv software. Yes, is that the plan? Yeah, to convert a heap of DICOMs to BIDS directory with a set of heuristics.
Chris, could you give Satra the microphone?
No.
Okay. No psychedelic dances on the side.
Yeah, when does this? Oh, sorry.
Wow, that's too big. All right, we're going to do a couple of things. So Chris talked about BIDS, and most of you probably deal with your imaging data in DICOMs. So one of the things that Michael Hanke, who's in Germany, and I worked on a while back, was to create a converter that took your DICOM files and converted it to a BIDS layout, made that process a little simpler. So we came up with what we call HudiConv, and it stands for Heuristic DICOM Converter. And the heuristic part is what really gives it the meaning of BIDS. So technically, if BIDS came up with version 2.0, which I was told was next week, you would be able to take this converter, update to that new structure, and be able to convert the DICOMs. Now, a few things to keep in mind. This won't give you a full BIDS data set that's valid with the validator. There are a few more pieces that you'll have to add. So this is a DICOM converter. This doesn't convert your experimental paradigm files yet. And that would be a nice thing to also have in a set of repositories, because people do use different kinds of software. So some people use PsychoPy, some people use Presentation, some people use ePrime. And these exist as cottage industries in terms of conversion in almost every lab, taking the output of these things and converting them into some kind of standard format. So that would have to be added to this. And then you need to add a few other pieces, which is metadata about the data set in a file. So here we focus on just the DICOM conversion bit. All right. So I'm not going to have you install these things today, but since this is the end of the week, you should be completely familiar with all of the things over here and be able to handle different things. There is a Docker container that's available, so that makes your life, you don't really have to install anything if you have Docker on your system. So that's one of the really powerful things about Docker, is that it allows you to do things that somebody else has created and maintained without having to install all the dependencies. If you were to install everything, it requires a few things. Miniconda, DICOM to NIX, that's one of the converters we use right now, although once Jalinda has MRI convert supporting BIDS format, that'll be added on as an additional thing that you can use to convert things. I'll talk a little bit about Git and Git Annex, just as another set of things that you should think about. Everybody here now knows Git and GitHub, right? That was prerequisite on day one. If after that, so you know that you're thinking about versioning code, and Git Annex is about versioning data. Data and code are just similar digital entities. It's just that one we can read in text and other comes in all kinds of different forms. But both should be versioned, and Git Annex is a way of versioning data so that you know exactly what version of data was used to produce certain things. So all we're doing over here is Jarek, who's been developing DataLad as a wrapper around Git Annex, provided a phantom data set that is available as a Git repo. And so I get that data set, and then, okay, forget this part. This part is only for running QtConv on it if you were installing things yourself. But what I can do is, now that I have this Docker container, NiPy QtConv, I can mount my local data. So I'm assuming that my local data, which I've just grabbed over here, exists in $pwd. You've also gone through Unix tutorial, so it's very easy to do this at the end of this week, because I can assume all kinds of things that you should know. So you mount it to a data folder. Here is the Docker image or container that you would end up using, and then you point to your DICOM files. And you can notice a couple of things over here. This is not a full path to a file, it's a template for a path. So this %s, you've also seen this earlier on Monday, is a string substitution that we will use to fill in with a subject ID. Now, Chris will tell you this is never going to be a valid BIDS data set, ever, if I use that subject ID. But for the exercise of thinking about DICOM conversion, we will use that subject ID because that's how that data that Jarek has is situated. We can change it to a different subject ID quite easily. You would just need to change an internal folder there, here, call it by a different name, and then you can use that name over here. Okay, so what are we pointing to? We have a data structure with a subject ID and all kinds of folders pointing to a set of IMA files. Now, for those who know different kinds of DICOMs, IMA files are just Siemens DICOM files. And then we apply what we call a heuristic. And this is a default heuristic, so if you go to the QtConv page, it comes with a set of heuristics that somebody has created by default. So one is this convert all heuristic. It basically says I'm going to convert every DICOM file I find in groups into nifty files. Finally, the other pieces. I want to use DCM to NIX as my converter. In fact, that's the only way this DICOM converter, the Docker container, is going to work right now. There are other converters it can use, but it's highly recommended because it's fast and it supports this flag. This -b flag is magical. It's called the DICOM create the BIDS JSON file automatically when you're converting these DICOMs. And finally, we say where to store the output. Okay, so running that Docker container will convert that data, but it'll basically convert your entire data as single nifty files for every group that it finds. So your resting state run will be one file. But you may only want to convert a few things or some things or organize it in a better way. And this is where you can extend that heuristic file to give you a layout option for your DICOMs. So So here I'm going to take that data set, which has all kinds of data, and I only want to convert the T1 and the resting runs. You could convert everything else, but just as an example, we're going to only convert these two. And if you start looking at this, now this will, once you get familiar with the bid spec, will start appearing like bids compliant layouts. So there's an at folder in which there's a subject and there's a T1W, because this is a T1 weighted image that was acquired in the scanner. There's a rest folder which is in func, you have all kinds of things, and you get the run, item, bold. So all of this now conforms to expected bid structured layouts. And again, if you wanted to go and look at something that has a full thing, so here, for those of you who will end up using HCP data collection protocols, there's a CMRR heuristic, which basically shows you a bids data structure layout for all different kinds of things, including field maps, resting, and task data. Okay, so what are we doing over here? So this heuristic file, I'm also going to assume that you guys know a little more about Python by the end of this week than before, are a few things. So you create these keys, which basically say these are groups of files that will be named according to this template that I've created. And then this heuristic file gets as input a list of grouped information. So let's take a look quickly at what that information looks like. Let's also do last row, still visible?
Yes.
Okay. I'm going to try and make this a little smaller. So when you run Huricon with the convert all option, it will create this dicom info.txt file, which is grouped dicoms and gives you very basic information. Tells you XYZ, number of time points, few things with TR, gives you the name of the sequence that was used, and gives you the name of this false and true for at least those who are using Siemens machines. If you have motion correction turned on, it tells you whether it's generating retrospective motion corrected data or not. So this forms the input to this file. So each of those columns are these 12 fields in S. So you basically go through, and for every S you say, I want to do something with it. So in this case, the T1 was collected with 176 slices, and it had one time point volume. So for dicoms or MR sequences generate all kinds of different data. So we can't cover the entire space, and that's one of the reasons we are looking at heuristics to inform you given the scanner that you are acquiring data on. So if you used a multi-echo MPRH, instead of getting one, you might also get another series which has 4 volumes, and that may not be useful from the perspective of what you want to do. You might want the RMS version, which is stored as a separate dicom entry in the output. So this basically says attach to that T1 this sequence, and then this goes on. So you create this heuristic file. The second thing, this was a dummy task, so it's really not a very long task thing, it's a phantom scan. It had 15 volumes. So I can use a logic which says I want a sequence that has task rest in the name, and I can get that from that dicom info.txt file. I know all the names of every group, and I say if it's over 10, and I want the motion corrected thing, so I check on that last column, which is the 13th column in this. If that's true, then I append this item. What this also allows me to do is create additional keywords and labels to fill in to that name. So ACQ is a variable that I've created in that template, and whenever this runs, corrected will be put in there in the case of ACQ. So this allows you to create various customizations that would support the kinds of bids, naming structures, and conventions that are allowed. And once you do this, Exact same command. We've just replaced that heuristic file with this new heuristic file. So that gets you from DICOM to BIDS, and if we look at this, you can see that we have the BIDS output created for those two files. We have the inat, we have the func. We also have some additional info that BIDS won't care about, but it's useful to keep around. The heuristic that was used to convert things, as well as this. And then you can take a look at the JSON file. So I'll take a look at inat. So at the beginning, it'll have all the required keywords that BIDS requires, but what Huriconv also does is extracts all the other DICOM parameters and sticks them as key value pairs into the JSON file. So if you had to look up other things that weren't in the original DICOM file, but not captured in BIDS, you can get at it. This will still pass the validator for BIDS, because BIDS validator checks to make sure that you have the required keys from BIDS in there, but it also has other information that may be useful to you. So for those doing MR physics work, Mr. Phoenix protocol, or MR Phoenix protocol, is actually quite useful to know exactly how coil combinations and other things happen, and that information is available there and there. That's about it. That's how you convert DICOM to BIDS. And now you have a Docker container to do it without having to download any piece of software. Okay. All right. We have another half an hour. So you're not, yes?
Can I ask a question? This might be for both of you. So sometimes you're in a protocol, you only mean to acquire one like resting state image, but like the kid squeezes a squeeze ball, and so you stop one, you start it again. How would that, so you'd have kind of two DICOM folders that have lots of the same information, but they're different scans. How would that, can you talk through how that would sort of appear in a BIDS kind of directory?
So great question. So maybe I can repeat. Sometimes we interrupt the scan for this reason or another. Basically, we want to discard some data.
Keep talking.
Hello. We're so close. Okay, so we want to discard some data, and there are two options. You can keep everything, even those sessions that you don't intend to use, and they were basically mistakes. They are shorter, and those are just extra runs. Or you can basically, when you convert stuff to BIDS, you also make a decision. Basically, you do a rudimentary cleanup. So you remove things that are not intended, that you don't kind of approve of. You know, this was an interrupted scan. I don't want to use it. I will not include it. So yeah.
Is there? So I understand that you could do that maybe if you had like the volumes, you'd had too few volumes or something.
Yeah.
Like that.
So.
Let's say it was an MP Rage and there was just like a really movie, like there was lots of artifacts in the structural. Is there kind of a manual step in which I go in and say yes, no, or something?
So yes. So basically, we're trying hard to build tools to automate all these things. But quite often, when you do any data analysis, you would keep a log. And you would say like, oh, here the subject was drunk, I want to discard the subject. Or there was too much movement and other things. So manual steps in data management and cleaning are inevitable. And then basically you would go in and you'd look at your nodes and say, okay, I want to discard this extra T1 because that was the bad one.
I'm just wondering, so I think it sounds like you would do that after it was already in the BIDS sort of folder structure. And
that might be easier, basically.
Would you recommend like deleting it, or is there a flag in the JSON that says I care about this, I don't care about this? Like, is there a workflow for that already?
We haven't thought about this this particular use case for dataset we've dealt with so far. basically bad data would not be part of the final product. Yeah. So we just basically remove it and keep it this way. Yeah. But maybe there is a need for like keeping everything and flagging something, just like do not use them. But so yeah, in current way, you basically just remove stuff that you don't want to use because it was bad.
Bits 2.0 next week, we'll have that.
Exactly, ready to go.
Okay, are there any questions? So, Christy, in talking about your point, you could also do it at the level of this heuristic.
Yeah.
Because you can view DICOMs and you say, or you know something based on your lab notebook as you were acquiring data, then you can incorporate that in the heuristic at a subject level, saying, this is what I want to do with this subject. Okay. So the other piece was going to talk about NiPipe. And we have 25 minutes. So you're going to get the world's quickest introduction to NiPipe. We'll see if we can do this online, hands-on, in 25 minutes. It's going to be hard, but we'll try. So here is a set of Jupyter notebooks that Michael is creating, and I use the word creating in the present sense because it's not complete, but this is a rewrite of the extensive NiPipe documentation in what I would say more humane manner. Maybe not human readable, just more humane. And he's done a fantastic job, but he's reached up to data output, which means the rest are works in progress, and you can give him information or feedback, or you can even contribute to these because it's just a GitHub repo that he's building. All of these other things exist as existing documentation. It may not be as humane as Michael's documentation. But we'll go through some of these things very quickly. Okay. But the first thing I'd like to do is pull this up as my binder. Yes. It's in Slack. And Jeremy didn't quite go into my binder, but he talked about it when he gave his talk. It's a service he provides to run notebooks in the cloud. A couple of things to keep in mind. You can't do your entire analysis on my binder. It is a free service. It is a good service. You can do a lot, but don't think about replacing your computer with my binder services tomorrow. But you can use it very effectively for all kinds of tutorials, and it might take a little while to load because everybody's trying to load it right now. But hopefully it'll load. And if somebody has loaded, I can just refresh it and it'll load a little faster. We should also ask Yarek if fail to ban detects simultaneous connections to a single thing and bans all IP addresses. We'll see. We'll see.
Somebody find me my computer. I'll fix it in like 10 minutes.
Okay. Well, while it's loading, I can do a few things. So what is NiPipe? NiPipe is a framework written in Python allowing you to integrate any kind of tool into a data flow pattern, which means every tool has inputs and outputs. Luke has a nice presentation that you can look up that he gave a while back in Boulder, I think.
Really just cut and paste Satra's.
But everybody who does, but everybody who does a presentation based on my slides makes it more humane. So it's always good to read other people's presentations of the material. Anyway, it has extensive support for all kinds of tools. So let's look at the set of tools. So this was the existing documentation, and all of it is there. It's just a lot of documentation. In terms of interfaces, it supports almost all common analysis tools that you end up using. If there's something that's not here, you're welcome to provide new interfaces for it. But likely, we, I think, even follow maybe the 90-10 rule or 95-5 rule. We really cover a lot. So there is a lot of interfaces and pre-built workflows for doing various kinds of things, and a whole lot of examples for different kinds of analysis that you want to do. Okay, how's this doing? Anybody?
Failed.
Failed, then I reloaded it, and then it worked.
Okay, 1, which means it's going to load a little quicker. I think they do cache the image that they build, but we'll see. This was Ariel's question, how stable is my binder? For okay. Anyway, so while that, we'll come back and see if it failed again. What are the kinds of things you can do? Why did we create NiPipe? Because we found that there were tools out there that did certain pieces of your processing pipeline better than others. So we wanted a way to patch these things together, and that was usually a hard thing to do. You had to make lots of assumptions and lots of other things. So here's a course example. It's just meant to schematize what NiPipe can do, but the general idea is there, that you may want to combine things from different packages, and that was hard to do at the time when we started the project, and NiPipe makes it easy. The general layout of something like this is that you grab your data and you want to sync it somewhere, but then you pull up these different routines, and they now are just simply Python. Yes?
What do you think of, like, obviously the point of NiPipe is to effectively alternate between other, like, existing packages like SPM and FSL and whatnot. How does that fit with the other idea of picking and choosing which thing you're using? In the case of, say, where 3D Plus Sim had a bug that made it, anyways, changed that.
Fits right in. You can replace that step with something that may not have a bug.
Well, I mean more the other side of that. Let's say I use an approach that alternates between different things, and then someone critiques why using this. Let's say I didn't pre-register. This is the exact process I want to use, and like I pick and choose, and they might view it as an arbitrary way to make it better.
Maybe I can take this one. Using only AFNI in your workflow before this bug was fixed didn't make 3D class work better.
Sure, right.
So it's not about pick and choosing. It's about choosing something that that is appropriate for your task. It's the criteria you use to choose your tools. Cameron seems to have
I mean, I think that exactly, I mean, correct me if I'm wrong, but I think the point is you know, an example that Russ gave was where somebody was using AFNI for 3D Plus. You know, it's kind of giving this impression, well, you're specifically choosing this tool because it gives you better results, and isn't it odd that this is kind of where the different tool that they use, right? So is that more what you're getting to, Chris?
Right.
How do you go with
Okay.
this?
Let's say I didn't know that the thing I'm using was a bug because I think that's a better assumption, at least as a starting point. But if I'm going to use different packages for different parts of the pipeline, then someone else critiquing that.
Can we do this over lunchtime?
Sure.
I think it's better.
Okay, so I'll answer that very quickly, and I think it goes back to what Russ said. So you're talking about optimizing a workflow to look good by choosing things that match up something you want to get at the end of the day. What NiPipe is about transparency. The fact that you've optimized it, if you release that workflow, people can take it and replace that workflow with other reasonable things, like Josh Karp did with a bunch of different things, right? So, and that would build up a confidence level on your particular choice of method, how extreme that may have been or not, right? So it allows that kind of flexibility for a couple of reasons. So what this allows is you can choose things, but everything now becomes a Python function. So every interface, whether it was written in MATLAB, in C++, in Java, or anything, is accessible as a Python function. NiPipe does not re-implement the function in Python. What it does is provides access. So you still need to have these underlying tools available on your system. So you need to have SPM and MATLAB, or the MATLAB common runtime if you're running in the cloud and you don't have a MATLAB license. But NiPipe will allow you to quickly switch between those two if you're using SPM in the cloud, running NiPipe workflows. And then the general idea is that you connect these things as a data flow. If you think of all of research as a data flow, data comes in, data goes out. Then NiPipe enables that kind of thought process by allowing you to move data between interfaces. You still need to understand neuroimaging. NiPipe is not a replacement for that. Although with things like BitZaps, existing workflows, you could say somebody has crafted a pre-processing workflow for me. I'm going to point it to a BIDS data set, and I'm going to trust this workflow as doing the right thing. Okay. Are we? This is still. Okay. How many people click reload as soon as I click reload? Okay, so what we are going to do is we're going to open and upload a new notebook. And the intent behind this notebook is that, and this notebook was also pasted in the Slack channel for those who are playing with it, is to approach NiPipe completely from the flip side. This has nothing to do with neuroimaging. It's just using the workflow framework in NiPipe to try and demonstrate how you can connect things. And hopefully, the simple Python examples will allow you to say, okay, I understand these things. You guys are all doing neuroimaging. So knowing these tools is part of your job. This part is sort of new because this allows creating and connecting things. And then this part is somewhat extraneous. We are not going to go into details since this is the world's quickest introduction to NiPipe and we have 15 minutes left. There is existing documentation. You can go through extensive tutorials that Michael is building. And this is something I came across yesterday. Somebody took the entire GitHub repo of NiPipe and created a visualization of contributions to NiPipe over the last 6 years. And it's a fun visualization to watch. You see Chris jumping around from one end to the other. That's why it was really a lot of fun. Okay, so let's run through this. This is an active thing. I'm going to import OS, which is a Python OS package, and a couple of things from NiPipe. This concept of a workflow, a node, which are constituents of a workflow, and a function. And as you can see in the second thing, what I've created is a simple function. It adds A and B. Everybody can see what it does. And I can wrap that function. So this could be a function which uses URL lib, which you've come across in other tutorials over this week, and could use if this then that and trigger of coffee making as well somewhere. So you could do a lot of things when you are allowed arbitrary functions. But that's the key point, that you can use this for doing almost any kind of arbitrary computation. So this function node has a couple of things which says I need to know what the input names are, I need to know what the output name is going to be, and what function I'm going to use. Within this node construct, this node is given a name, A plus B. You can't have two nodes with the same name in an NiPipe workflow because it then gets confused as to what you mean by it. And I call this a variable here called adder. And I set inputs to that variable, A and B, 1 and 3. I add it to the workflow. I set where the workflow should execute, and I run. Okay. So far, so good. And 1 plus 3 is 4. You could run it a few times and you would get the right result. But the general idea is now we've created a container for data processing. Okay, so I call that the hello example, not the hello world example, because the hello world example in NiPipe requires 2 nodes, because you want to move data from one node to another. And that's what we're going to do. We're going to define another arbitrary function. It's called concat. It will concat the 2 numbers into a list. So again, it gets some input names because those are the input names. Output name is some list. I don't care really for this purpose of the demo. The function is concat, which is that function. And I've created a new variable and a new node. Now I put this concatter input B. So let me go through a thought experiment over here. If I run this now, for those who haven't run it yet, what should come out? So what have we done effectively? We've taken one node which does addition, and we're connecting the sum, the output of that node, to the input A of this node. And what does this node do?
Return for 3.
Return for 3. All right. So we'll decompress that in a second. Your sum list is 4 and 3, and now my workflow has 2 nodes, right? And it demonstrates a couple of things. You can take data out from one node and put it into the input of another node. Okay. All right, we'll do one more thing. So that output is 4.3. I'm going to add another node, and this is again a simple Python thing. So how many here feel reasonably comfortable with basic Python? Actually, let's put it this, let's flip that. How many here don't feel comfortable with basic Python right now? Okay, that's a good sign at the end of the week. Okay, so what's likely to happen when I add this node as following that concatenation node? So my concatenation node produced a list 4,3. I'm adding this node, I'm connecting the output of that to A, and look at what this node does. It adds 1 to a list of numbers. What's going to happen? Unfortunately, Python isn't that intelligent. So Python will actually result in an error over here. Let's see what NiPipe does. Oh yeah, we got an error. So when NiPipe generates errors, it creates a crash file. And there's a useful tool called NiPipe display crash. And since there's only one crash file, I'm going to not print that out fully. And I'm going to say, show me. And it tells you everything about the inputs that went in, gives you the traceback, and then says concatenate list, not int to list. So we can't add 1 to a list, but we really want to add 1 to list. So there are a couple of ways of doing this, right? But NiPipe has a separate construct when you want to do a single operation. So how many people here use FSL? Almost everyone. Bet, if you ran bet on 10 images, would it work? No, you'd have to write a for loop to run it over 10 images. This map node construct in NiPipe simplifies that concept. What I'm saying is I want to use this input A as an iterator. I want to run over this and apply the same function, +1, but now for every element of this input. And remember, the input that was coming in was some list, 4,3. So hopefully, when we run this version, gives us 3 nodes, we get what Christy was expecting, which is it takes each input, adds 1 for each one of them, combines it back. For those who are in Jeremy's tutorial, he talked about map reduce as a concept. How are we doing? 5, 8 minutes? We're good. Okay. So this maps out each thing. You could replace map node with a PySpark kind of idea here. It distributes each element, does some operation on it, grabs it all back. And that's what a map node does. Okay, all right. So that was good. But NiPipe has this other construct. You often end up in this case where you have 100 subjects that you want to run. Okay, we start with 30 or maybe 100, or in the case of the Human Connectome project, maybe 900 subjects that you want to do things over. You don't want to write a workflow for each one of them. You want to just for loop over a workflow. So you could define a workflow for a subject and write a for loop around that subject. Completely fine. But NiPipe has this concept called iterables, which allows you to iterate over parameters of a node. Now, let's say, going back to that extensive thing, I wanted to replicate Josh Karp's work, where he used different kinds of functions, different kinds of parameters. What you would end up writing as a script are multiple for loops at different places, trying to execute over different things. We can do all of that through iterables, and we'll get to that in a second over here, but let's look at the effect of one iterable right here. So what I'm saying is that adder, which is my first node which does addition, the inputs are now a pair of lists. It's still adding one thing at a time, right? But I want that whole workflow, that subgraph, to repeat over 2 inputs. So I'll run it. NiPipe has a way of generating graphs to help me look at things. From IPython, I'll import image. This is my simple graph. It says I've got 3 nodes, very simple workflow over here. But I can now look at a more detailed graph. This was the execution graph. And you can see 2 parallel workflows, because now I have operated over 2 sets of inputs. That's what that iterables function, iterables over here said. I want to run this workflow or the subgraph of this node adder over multiple inputs. Okay. I can add iterables anywhere. So this graph has concatter as the second node. And let's say for some ridiculous reason I wanted to operate over multiple values of B. A practical example, neuroimaging. Smoothing is actually a function of the match filter theorem. So if your smoothing is optimal, you're going to detect things that had the kernel resolution of that smoothing kernel. Right? So you may want to smooth over multiple things and aggregate information from that. So it could be that this concatter was a smooth node in an experiment and you wanted to smooth over multiple levels. So you just add that parameter, give it a set of values, do the exact same thing, write the graph, and now let's look at the detailed execution. So we have 2 levels on the first node, 2 more levels on the second node. So we expect the total number of outputs, being a cross product of those things, to give us 4 outputs. And that's what you see. You have 4 outputs over here. And they're kind of operating in parallel because you have the first set of iterables on the first node. Okay. So now we've expanded things out. But we may want to pull those things back in. That's where NiPipe has another concept called the join node. Remember, this is drinking down the water hose in 25 minutes. So hopefully you'll be able to play with these things in your own time and get different understanding. But we are hoping that at least the concept, the main concepts of workflow design are here. And then you can replace this with elements from your brain imaging workflow. So what a join node does is basically says what I want to pull back. And in this case, it's saying, remember that adder node where I had iterables over its inputs? I want to collect the variations of those inputs back into it. So here we had 4 outputs. These outputs are an interaction between adder and concatter, right? I only want to bring adder back in, which means that this, if I run it, should give me back 2 outputs. I still have the variation among concatter. Okay, a few more things to talk about conceptually. Here, I'm bringing in NumPy into the picture. And you can notice that I'm importing NumPy inside this function. NiPipe has no state maintenance that you might think of when you open a Python terminal, because one of the things NiPipe can do is send your code over to a remote workstation to run on. So it needs to figure out what sort of things it needs to import over there. And that's one of the reasons you have to do your imports within the function as opposed to a global import outside in a Python script. Because this function could get executed in some remote cluster somewhere, and it needs to know how to do the inputs. But effectively, you can do anything. I was hoping I could get to an if this then that example, but that didn't quite work out. But anybody who comes up with the first if this then that example, how many people are familiar with if this then that? 1, 2, 3, 4. Okay, so I rely on you to come up with an interesting if this then that example for NiPipe. It's a service that allows you to send web requests, and it basically allows you to create web workflows of different kind. Okay, so I do this, and now I have a whole lot more things because I am expanding it out and then concatenating it back together. I generate the same graph. At the simple level, it still looks like a simple graph. I've just got 4 nodes that I've created. The slightly more complex level, we had that expansion up to 4, and then it gets combined back down to 2 because I'm merging things between 2 of those outputs. Okay. All right, so that's workflow construction, and I leave it to your imagination as to what kind of functions and interfaces you could put in there. But this is the basic of workflow construction. Next piece is that this run function, which we have just been running over there, is what's executing this thing, has many plugins. So you might be on a Slurm cluster, you might be on an SGE cluster, and NiPipe has support for almost all plugins that I can, all major clusters that I can think of. Using NiPipe plugins. So we have support for, forget the first three for a second, IPython, SG, LSF, Slurm, HD Condor, or if you have a cluster that's not listed over here, it's very easy to, but I would think that that cluster, that set.
What about AWS?
That's not a scheduler.
That's not a scheduler. So if you use Star Cluster, which Cameron went through, you could run it because now you get SG or Slurm as a scheduler over there.
You can experiment a little bit with provisioning system, and it still seems that there is quite a bit of extra work for setting up those machines and those keys and etc. etc. It would be nice to streamline all of that, but it would be nicer just to capitalize on another project that already sets up a cluster for you in the cloud. But the one that we looked with Cameron this week, the CFN cluster, it's not newbie friendly. But yeah, that would be really cool.
And other things you can think of is, so if you're using Slurm, for example, it can expand out to AWS if it runs out of cores locally. So you just need to give it a credit card number and or actually you don't give it a credit card number, you give your account, which indirectly has a credit card number. So that allows you to just use Slurm, and behind the scenes, Slurm handles the execution on AWS. So there are different ways, and you should continue to think about how to hack with things. So different ways of approaching the same problem. Anyway, there's an extensive list of workflows. Multiproc allows you to do things on your local computer with multiple cores. If you think of some of the nodes that we have now, they have 48 cores on them. I think the latest sets of nodes that have come out have 40 physical cores, so about 80 hyper-threaded cores that exist on some of the cluster nodes. So you can do a lot even within a node without having to go across doing things. So the multiproc plugin, and then Cameron's group has created a bunch of nice extensions to it, allows you to take advantage of that. So you just say how many processes you want to use, you give it the workflow, and you run. And let's take a quick look at it. We are going to time this. And it took 108 milliseconds. And this is another piece of NiPipe. It actually didn't do any computation. It caches the working directories of every node. So if the inputs haven't changed, it won't recompute. It just picks up the information from it. So now I'm going to change the location where it's computing by changing the base directory of the workflow. And it takes 270 milliseconds because this was a very simple workflow, so it didn't have to do a whole lot, but it took a little more. Now I can repeat that in that location again, and we're back down to 104 milliseconds because it's not doing anything other than picking up information. So this is the data flow framework in NiPipe. If you go back to the tutorials, these concepts pages go into more neuroimaging oriented approaches that would be more applicable to your actual needs. But the data flow framework, once you understand those basic concepts, then you can start plugging in all kinds of interfaces into it. So we're not going to go through it. I'm just going to pull this up. And it goes through how, in this particular case, how you might use BET within a shell or in an NiPipe framework just as a Python function, and then it extends on as you go into workflows how you would use this within the context of a workflow. So this is a flavor of how you can optimize your analysis to be reproducible and repeatable and more efficient if your cluster storage methods allow it. NiPipe, we think of it as a Swiss Army knife of tools, and it provides easy mechanisms through which you can compute on data. The other reason of showing that workflow example with just function definitions is that it was intended to say you can write anything, you can do anything, because those are arbitrary Python functions. You just have to know what inputs they take, what outputs they get. When you write more formal interfaces in NiPipe, you get the benefits of type checking and other things that come in. So if an input required a file and you were to give it a value 4, it would complain that no, I'm looking for a file. So when you start using the imaging interfaces like BET, you can't give this a non-existent file, for example. That in file will want that file to exist before you can run it. What the data flow framework allows on top of it is that file might be coming from the output of another node. So you don't have to know the names of the files. You're just connecting one port to one output port to one input port, and that's how you create connections. All right, I think we need to head out. So
No heading out.
oh, no heading out.
But thank you, Chris and Satra. We can do one more thing before lunch.